short section of notes. So far, I received a bit of emails from some of you about the fiasco, which was the internet last night, and that's fine. Things like that happen, okay? But so far, from the quizzes that I have graded and gone over, they're looking really good for dimensional analysis. They're looking really good for scientific notation. So well done. If you ever get stuck on that kind of stuff, please ask me. Okay? But we did well enough to where I feel like we can go ahead and continue our discussion. So, again, section 3 is going to be split into two parts. And we start off by talking about accuracy and precision. You heard me say the word accuracy as I was talking about our measurement of the length of the walls here, length of the room. Okay? You might also hear people use these terms interchangeably, which at the time it might seem like it's correct, but that's why they're two separate words, really, is because they are different. Accuracy refers to how close a measured value is to an accepted value. So that's why a lot of times when we're talking about accuracy and precision, we like to use targets, okay? Where the bullseye is the accepted value, all right? Precision refers to how close a series of measurements are to one another. So in science, this has probably been preached to you numerous times, is when you run an experiment, you don't really just run one trial. You run trial after trial after trial, because you want to make sure that your plan, your procedure, your calculations, your measurements, you want to make sure that they're all consistent and that you're getting the same and consistent results after every trial. But if you start getting these trials and they are having these results that are just all over the board, well, you're not going to have a very precise procedure and you're going to have to modify it. So if we look at these 4 examples here, in this left one right here, we have a single arrow right smack dab into the center of that bullseye. We only have 1 arrow in this one right here in the bullseye, so we would say that that particular arrow was accurate. But now let's start shooting some more arrows at it, okay? This second arrow from the left, it has 3 arrows on it. Sorry, the target has 3 arrows on it, nowhere near the target, or the bullseye, okay? But they are grouped together. So after each of the shot from the arrow, we had the same result. So since we have a grouping of those arrows, we would say that those were precise because they are right there next to each other in value. However, they're not accurate because they are a decent distance away from the bullseye, which is the accepted value. Third target, we've got 3 arrows right in the middle of the bullseye. So then we would call that precise and accurate. Because not only did all 3 of them group together, but they grouped together right in the middle of the bullseye. And then our last one here, we have 3 arrows again, but this time they are all spread out over the target, not a single one in the bullseye. So that is neither accurate nor precise. Other examples. I added something to the slide. Okay. This is a table of measured densities, okay, of an unknown solution or unknown substance. Okay. I put a little star in here because this wasn't included in this table. It's included in the table on the next slide, I believe. But the actual density of this substance is 1.59 grams per cubic centimeter. Okay. And in order to really gauge accuracy and precision, as well as what we are going to calculate percent error, you have to know the actual accepted value. So if we look here, of these 3, which student had the most precise measurements? So again, we're looking for a student who had the most precise, meaning the most closely measured values to each other. So student A has 1.54, 1.60, and 1.57. Student B, 1.4, 1.68, 1.45. Student C, 1.7, 1.69, 1.71. And of those three, who had the three measurements that were closest together? C, senor. Yes. Student C, very small deviation, much smaller than the other two. Okay. Now, who is the most accurate? You say A. Why do you say A?
Because the average is closest to the actual density.
There you go. The average down here is closest to the actual density of 1.59. Okay, its average was for student A was 1.57. So you got two separate answers, or two separate students who had a differing measure of precision and accuracy. So they are not one and the same. So, you know, that's one of those situations where I still catch myself. I'm like, did I use the proper term? And I try to, you know, practice what I preach on this stuff, but sometimes it, you know, kind of goes to the wayside. All right. What we're going to be doing today is percent error. Okay. And what this is, it's defined as the difference between, it's supposed to be not and, but cancel that D out there, an experimental value and an accepted value. When we say experimental value, we mean what we measured in the lab during an experiment. Okay. So how do we calculate error is by this. Okay. The experimental value minus the accepted value. But for percent error, we have to add a few more things, and that's where you get this equation. I have actually kind of even broken this one down a little more clearly, if that's correct English. Okay. First of all, what do these bars mean? These vertical bars on either side. What mathematical term does that mean?
Absolute value.
Absolute value. And when something's in its absolute value, that means that no matter if you're subtracting a large number from a small number or what, you're always going to have a positive value outcome. Okay. And so here's how you calculate percent error, again, using the way that I have written down here. You take the absolute value of the measured value minus the actual value. Sometimes your actual value is going to be bigger than your measured value. That's why you have the absolute value sign there. So you take that difference, divide it by the actual value again, then multiply by 100 to put it into a percentage. So obviously, the smaller the percentage of error, the more accurate your results are. So again, that is the formula that I recommend you using. This one right here doesn't quite go in there. I mean, it does a little bit, but you kind of have to use a fancy word here, extrapolate, meaning take something from over here and put it over here. Okay, so I just went ahead and wrote this down. So if you want to get that written down, by all means. So let's look at some practice questions here. We are to calculate the percent error of all three of student A's measurements. Okay, so we're going to look at trial 1, trial 2, and trial 3 of student A. So you're going to need to have your calculators out. So I'm just going to kind of rewrite some of this information on here. So I'm going to go back and forth here. And 1.6 and 1.57. Okay. And the actual is 1.59 grams per. Okay. So we're going to calculate percent error for each one of these three trials. So let's look at trial 1. Okay. So again, absolute value. What is our measured value for trial 1? What is our measured value for trial 1? It's going to be It's 1.54. So absolute value, 1.54 minus what's our accepted value or an actual value? Very good, 1.59. And you notice that I'm not putting in the units in here, okay? If you want to, you can put the grams per cubic centimeters in here. Mathematically, they would cancel out before. They're not included in your final answer. So next, on the very bottom, you get the actual number. Okay, 1.59 times 100. Okay. So what is the actual percent error for number 1? I want you to calculate it. And here's why, because I don't have mine calculated right off the bat. So the whole thing, 1.54 minus 1.59. And again, you're obviously taking a larger number from a smaller number. So you're going to have a negative sign here, but it doesn't matter. Okay? So you have the absolute value in here. Divided by 1.59 times 100. And you can just put percent if you want to. That's what the 100 does. If you want to put percent right next to 100, that's fine. But so your percent error for trial 1 was 3.14%. Okay. And so we have to do the final 2. And so we do the same thing. Okay. Absolute value of our measured value, which is 1.60. Okay. That's in our data table. Minus the actual value of 1.59. Close the absolute value. Divided by the actual 1.59 times 100%. 0.62%. That's a percentage sign. And then lastly, do the third trial, 1.57, which is our measured value, minus 1.59, which is the actual value, divided by the actual value, 1.59, times 100%. We say 25? 1.25%. And that's what you're going to be doing for homework this evening. Now, there are other variations of this type of question to where you'll see on your homework I'm not assigning you to do. So for tonight's homework, you are not going to do questions 9 or 10. You can take a look at them if you want to, but we are not concerning ourselves with that type of question, okay? Where you have to determine what one of these values is. So you have to do a multi-step algebraic setup to solve for it. Questions on percent error. Okay, so again, I'm going to hand this out to you. Cross out questions 9 and 10. Put your name on it, and you will submit it to Classroom by tomorrow evening. If you get done with it today in class, well, by all means, get it submitted as soon as possible. But again, tomorrow, you will need to have your notes, calculator, non-cellular device for a calculator, okay? Because we're going to be having a homework check, you're welcome, / quiz, whatever you want to call it. So, you pass this over to Mr. Dale, maybe. Maybe.
Jacob never.
Wear shorts on Sunday. There's no on Sunday. You're going to be a little brisk.
It is supposed to snow.
It's supposed to snow a little bit Saturday night, I think, but high of 6 on Sunday.
Sick.
Low of -5, not including wind chill.
Hopefully it melts.
Ice fishing.
It's gotta be
It's
cold.
gotta be gross.
One day. Or we should take the roller out on the farm.
Love weather. I'm an old
Why
man.
not? Jake and I
You gotta plan accordingly. How old do you think I look, Mrs. Stevens? Well, thank you for that. I'll be 39 in May. Maybe just by looks, but not by regular body function because it hurts getting out of bed. All right, so those of you at home, thank you for joining. If you have any questions, ask me. But you may sign off now, and don't forget to get on Google Classroom to do your homework.